In this final lecture, I'm going to introduce the brand decoding. I think this is the first time and the only time in this course that I have chance to introduce the brand decoding to you. In this field, brand decoding field, there is a very important technique we called MVPA, in full name multivariate pattern analysis. For this topic, actually, we are going to apply the so-called machine learning approach to classify or perform some regression analysis to understand whether we can use fMRI data as the basis to predict or to differentiate the mental state. Okay, so in this part, I'm going to give you the brief introduction, the basic idea, and then we will use one of the toolbox called Pronto toolbox to perform this kind of analysis. So again, please visit my website and download the handout and materials from this week, week 15, brand decoding MVPA right here. And today's material is a little bit large, actually around 300 megabytes. And most of the content actually originated from this website. You can see this is actually the website of the Pronto software. So actually we download the demo dataset from the Pronto website. So if you want to see the original materials, you can visit their website and find the, I think the dataset. Yeah, there is a link called the dataset. You can find all the materials right there. So actually, the authors from the Pronto development team, they actually provide, I think, 3 or 4 different datasets, but today we only use the first dataset. And this dataset actually is the very important one because this is actually the same dataset correlated to the paper that published in 2001 in Science. This is a very, very important, the original article, the classical article, mentioned the basic idea about how brain can represent the external stimuli in a certain activation pattern or some kind of the representation pattern in your brain. Okay, so we call this dataset as the HEXB dataset because the original author that I mentioned in science paper is actually this one. Okay, so he's very important scholar in this field. So today we are going to use the Pronto software, and most of the Pronto software also use the core technique, basically the batch process technique from the SPN12. So again, you may need to include the SPN12 in your file path. And since again we use the SPN12, you need to follow the rule. There's no file name with the Chinese character or space should be allowed. Okay. And for the Pronto software, I think they already provided the most up-to-date version is version 2.1.1. So use this version, download this version today. This is the course map for this class. So now you can see we come to the very last part right here, the brain activity pattern. So the main focus is this word, not activation or activity, but the pattern. How our brain may exhibit a certain pattern to respond to a certain stimuli. For example, a picture showing on the screen, a cat picture or a dog picture. Even from the even focused on the same brain region, for example, the primary visual cortex, you may see different visual stimuli may cause different activation pattern. Again, the pattern is the most important word within this kind of a brain area. So can we use this kind of the pattern to differentiate the brain state or to predict or to say whether what kind of the visual stimuli that the current subject is looking at? That is what we are going to do. Okay. So again, this may involve the very important technique we call the machine learning or the classification right here. Or sometimes we can also perform the similarity analysis between 2 patterns with 2 different external stimuli. So that's what we can do in this part. So let's start from the very first part, the basic idea behind the MVPA, multivariate pattern analysis. So again, right now, the key sentence or key concepts right now would be, we are trying to look at the pattern of activation. Again, pattern is the most important thing. Within a certain brand area, of course, sometimes you can simultaneously look at several different brand regions, but this may make the analysis become very complicated. So sometimes we will have some kind of hypothesis. This kind of the pattern analysis may allow us to answer what kind of the stimuli that this person may seeing, hearing, or feeling. Okay, so this kind of the technique sometimes we call brand decoding. This is also named as the brand reading technique. So we can look at your brand and understand what you are thinking about. So it can help you to actually to use as a lie detector or something else. You can get rid of all the sentence, all the language that the people just trying to tell you. Just look at his brand, and you can figure out what he's doing or what he's thinking about. Okay. And this MVPA actually has a very important historical development. And originally, as we mentioned in this class, in the very first part, we are talking about the GLM, or sometimes we say brand activation analysis. And GLM sometimes has some technical term or more official term. We say mass univariate model-based analysis. If you may recall that GLM actually performed this kind of the regression analysis on each voxel within the brand region. So this kind of the voxel by voxel analysis, voxel by voxel GLM analysis, actually try to unravel or try to find out the optimal regression coefficient for different variant. For example, your study design for right hand grasping, left hand grasping, left hand grasping, or something else. So this kind of the exploit technique actually perform on the basis of voxel by voxel version. So you can see sometimes we will say GLM is a technique of the mass univariate. Univariate means a single variant or a single voxel. So mass means actually we have over 10,000 voxels within a brand file. So we will say this is a kind of a massive analysis on this kind of a new univariate model analysis. So you can see right here, I put the number right here is much more. It's around 50,000 at one time. That means within one human brand file right there. Okay. So you can see GLM is a pretty old or pretty historical technique that developed in 1995 by Carver Stone team. However, around 2000, people start to thinking about whether we can perform the pattern analysis on the pattern of the brand activation. In this kind of idea, there is a so-called MVPA coming out. However, in the very beginning, actually MVPA didn't represent the multivariate pattern analysis. In the very original paper that I forget about the name, they actually used the term multivoxel. This V is actually the voxel, not the variate, because now they try to search the pattern includes several different neighboring voxels within a region. So in this kind of the analysis, they say this is a multivoxel pattern analysis. However, this kind of MVPA approach can actually extend to different modality, not simply within the fMRI data, but also you can apply this kind of technique to EEG, MEG, or something else. So in that kind of a situation, voxel is not a proper term. You may say channel, you may say signal, or something. So in this kind of situation, they modify this kind of term a little bit from voxel to variate. So now you can imply the variate as the voxel, as a channel, as a signal, everything is alike. And as we may introduce later, that you will find out actually the original version of the MVPA is actually performed by correlation analysis. You will find out it later. However, around 2003, people come to think about we can apply the machine learning approach such as the SVM, support vector machine, to actually help us to differentiate two different mental states right there. So around 2003, this is the very important time point that actually we combine the machine learning technique with fMRI data to do so-called brand decoding right there. So let's start to explain why multivariate become that important. why we just follow the basic idea about the GLM univariate or single voxel analysis. We take these figures as the example. This is actually quoted from this 2003 neural imaging paper. I think this is actually one of the review article or technical article. It's very important. You can read this. Okay. And we take this very first figure, the figure A right here. You can see if we have a so-called ideal univariate situation. Ideal univariate situation means that you can actually differentiate two different stimuli by using a single voxel or by using a single variate. So we call this is the ideal univariate situation. So right here, we take two voxels. If we assume that actually there are only two voxels with our brain, or we only have the two voxels data on hand. So now we have two different voxels, or sometimes we say two different variates right here. So now you can see we'd like to differentiate two different activity right here. For the first activity or first condition right here, we say we display this kind of the human face to our subject. Okay, so another condition or another activity is actually we display this kind of the chair picture to our subject. So now you can see the difference is now this is kind of the human face versus object pictures right here. We'd like to see whether these two different voxels activation or activity, whether this activity can help us to differentiate whether the subject is looking at which of the pictures right here. Okay. So now you can see, just remind you that the color means something. That the blue means subject is looking at the human face. Red means he's looking at the chair. Okay. So now you can see, for either voxel 1 or voxel 2, you can see the brain activity is pretty different when you're seeing two different kind of pictures right here. So in this case, either you simply use the voxel 1 or simply use the voxel 2, you can easily find a very good threshold right here. I just cut the threshold right here. If I can observe, for example, for voxel 1, if I see the activity higher than this certain threshold, then I would say, or I would speculate, the subject is looking at the chair picture right here. If you observe the activity in voxel 1 is actually lower than this threshold, then I would say the subject is looking at the face right here. So very similar idea for voxel 2, only that the activity is in a reverse way right here. So in this case, you will find out if I put these two different voxel activity as the two different variant, and now I try to plot this kind of a scatter plot right here. The black samples right here are actually the baseline. For example, the subject is looking at a crosshair picture or some scramble pictures right there. Then we call this is the reference point right here. So as this reference or baseline point right here, you can see actually this kind of baseline stimuli didn't induce any voxel 1 or voxel 2 activity right here. So you can see the activity is pretty low for this axis, voxel 1, or this axis, voxel 2 right here. However, when you are inducing this kind of the stimuli, for example, the human face, then you will see for voxel 2, it will increase the activity right here. But for voxel 1, it may remain the similar activity compared to the baseline right here. However, another case for the chair, it may increase the activity in voxel 1, but maintain a similar activity in voxel 2. However, in this case, you can just plot out the histogram for these two different things. Either project this kind of distribution to this axis. That means we only use the voxel 1 to differentiate these two things. It's easily to find the ideal cutoff point right here. Even you project this kind of activity to this axis, that means you only use the voxel 2 signal or activity as the basis. You still can find a very good cutoff point right here. Okay, so this is so-called ideal univariate situation. That means you only need one ideal measurement or one single voxel. You can differentiate these kind of things. However, in the real world, this kind of the situation, I got to say, it will be very difficult to observe this kind of the ideal univariate situation. Most kind of situation is the multivariate analysis or multivariate situation. That means you need to combine several different measurements to help you differentiate the things. we take this one as an example. You won't find out if you right now you only use the one of the voxel to determine whether the subject is looking at the blue human face or red chair picture right here. It will be very hard to differentiate whether they have an ideal color point right here. Even for voxel 2, very similar situation right here. So in this case, it's pretty hard to only use a single voxel. But if you combine these two different voxels information right here, you will find out actually you can find actually a linear cut point right here. It's actually a little bit not a vertical or horizontal line right here, but this kind of the oblique curve right here means you actually need to take both voxel 1 and voxel 2 information into account. Then you will have chance to actually separate this kind of two different situation right here. So in this case, this is so-called bivariate situation. Okay, but sometimes things can become much more complex. For example, the boundary or the border right here becomes nonlinear form. Okay, so this case you still can find an ideal border, but right now you cannot use a linear separation. You need a nonlinear separation to help you differentiate these two different things. Okay, so with a very similar idea, you can actually extend this kind of the bivariate analysis to multivariate. For example, I take 3 voxels, 4 voxels, or even tens of the voxels into account. Then the dimension would become 2, 3, 4, or just anything that how many kind of the features or variables you have on hand. Okay, so this is the idea that why we try to introduce the multivariate to help us to differentiate or to perform the pattern analysis right here. Even the GLM is this kind of the classical approach. However, the major limitation for the GLM is they have the basic assumption right here. The basic assumption is that the correlation or covariance between voxels is actually not that important. Normally, for GLM analysis, they just ignored this kind of the covariance or correlation between voxels. So there is no way that we can discuss so-called the pattern within the brain regions right there. Okay, so the basic idea is that if there is any covariance between voxels that can be observed, this is normally originated from the noise. So they don't think this may be that important. Okay. So this is a reason that why GLM may limited by the this kind of the basic assumption or the model to do further pattern analysis or to do further statistical inference right here. Okay, so we say GLM may fail to capture distributed. Distributed means that it is involve several different voxels or involve a certain region within your brain. So GLM may not be a suitable tool to capture the distributed neural codes right there. And this code means the coding, that how our brain or how neuronal cell may take the response to the external stimuli. So when we talk about the origin of the MVPA, we definitely need to introduce this paper. This very important paper published in 2001 in Science, and the key author is the Professor Hexby right here. And this paper right now, I think is already been cited for more than 3,000 or 5,000. It's a very, very important one. So it's the crazy idea is whether we can use the brain activation pattern to tell whether the subject is looking at different things. However, in that year, they didn't have this kind of the concrete idea about differentiation of different stimuli. They actually try to observe whether different visual stimuli can induce different pattern in our brain. And in our brain means not involve different brain regions, but focus on a specific region. For example, in this paper, they focus on fusiform gyrus, okay, right here. And another one is the parahippocampal area. And as we already know that actually fusiform is a region that actually activated to the face stimuli. So when you see a human face right there, you will activate this kind of the fusiform gyrus right here. And if you are looking at the object rather than the human face, for example, house or the place, actually it may induce the activation of the parahippocampal region right here. So sometimes we say this is parahippocampal place area, PPA right here. So they also try to investigate whether the FFA, beautiful face area, and the PPA may exhibit different brain activation pattern when the subject is looking at different things right here. Okay, so they have a specific hypothesis. They want to focus on these two different regions right here. Okay. And actually, in their paper, they not only induced these 4 different stimuli, they actually induced 8 different visual stimuli right here. So you may have a human face, several different building or several different objects right here, and they also take the one of the random pictures. They call it as scrambled pictures right here as the reference. That kind of the meaningless pictures, but serve as the reference right here. Okay, so based on their hypothesis, if different visual stimuli can really induce different brain pattern, then actually you can use this kind of a brain pattern to differentiate unlimited, actually virtually unlimited number of categories. If they actually have the one-to-one relationship between the stimuli and the brain pattern, then you can actually do so-called brain reading right there. Okay, so this kind of the things is actually we call the topographical organized representation in your brain. So you can see this kind of representation will cause different brain activation pattern that exhibit a different topological pattern in your brain. So we can use this kind of things. Of course, when we say topological pattern, that means it may involve several different voxels activation within this area. Okay, so this is the basic idea from this paper. However, in that time, they don't have the idea about the support vector machine. They don't know anything about the machine learning, but they try to perform the correlation analysis. So you can take this picture. This is also the picture from the paper. So you can see they try to focus on the brain region that we mentioned, the PPA and the FFA right here. And you can see they try to calculate they use the main response value. That, for example, you already can observe the Baud signal or the preprocessed Baud signal strength as the reference. So right now, you can take the brain or the Baud signal strength across all categories as the reference. We calculate the mean value as a reference. Now you try to figure out when people are looking at this human face, what kind of the response may happen, or what kind of the Baud signal may happen right here. So you can see actually they will encode the color with the orange to yellow color means the positive value. That means you will have the activation level higher than the mean value. Okay, and if you use the cold value or blue value right here, that means you will have the activation lower than the mean value right here. So you can see when the subject is looking at the human face right here, you will see this kind of pattern. So you may see the anterior portion may have the higher value, and the medial posterior portion may have a lower value. However, when subject is looking at the house picture right here, you can see the pattern is very different right here. Okay, so now you focus on the same region, but you are claiming the pattern may be very different. So right now they perform so-called the spatial correlation right here. So you can see if we take different rounds as different sample, we may repeat the fMRI data acquisition. So you will have the several different rounds. For example, you have the 10 rounds on hand. Now you take the even rounds, for example, 2, 4, 6, 8, and 10 as one sample group, and other rounds as the 1, 3, 5, 7, 9 as another sample groups right here. You can perform the correlation analysis between these even and odd rounds right here. So this approach they called split sample. You just split the odd and even rounds into 2 different groups and perform the cross correlation between them. Then you will find out actually for the face stimuli right here, you can find a very high correlation coefficient between these 2 different samples right here. So even they happen in different rounds, you still can find a similar pattern within the certain region of the brain. And again, if you perform the cross-correlation analysis between even and other rounds when subject is looking at the house pictures right here, again you will find a pretty similar pattern right there. Now you try to perform the cross-correlation between 2 different stimuli right here. So you can take the even round human face stimuli with the other round with the house stimuli right here, you can see now the correlation becomes very low. And sometimes you may find they have the negative correlation. That means the pattern is pretty different right there. Okay, so the similar idea can also observe between the even round of the house and other round of the human face right here. So actually they didn't perform the machine learning analysis. However, this kind of the correlation analysis gives us a very important idea that pattern may really exhibit or may really exist in your brain. Okay, so it actually inspired the scholars afterward to think about whether we can use the machine learning approach to differentiate the different brain states when you receive the different stimuli right there. Okay, so right now I may try to transfer the problem to understand what people is looking at or thinking about to a technical term we call classification. Now we try to classify the brain state, or we try to classify what is the perceived stimuli right now. Okay, so the basic idea about the classification problem is that you need the sample data. For example, you need to collect several different rounds of the fMRI data, looking at the different pictures right there. That is called example, or sometimes we say sample data right here. Okay, this is very important. So for fMRI, actually the example or sample represents the experimental round right here. Okay. And another thing is if you want to ask machine to learn from the data, you need to give the machine the so-called feature set right here. So right now, the features within the fMRI data or signal is actually a cluster or a group of the voxel data set right here. So now, you definitely don't want to use a single voxel data, but you can actually input, for example, 10 or 20 voxel data set as the, for example, if you have 20 voxel, then you will have 20 features as the basis for machine to learn from these kind of features. Okay, so now you have several samples. Now you have the features. Then the problem will be how machine or which kind of the machine model may better help you to understand or to predict the different classes right there. Okay, so this is the basic idea or the essential elements that if you want to perform the machine learning, you need the samples, you need to identify the features, then you will find the proper model to determine the classes right there. So we take this picture, this diagram as the example right here. Again, when people is looking or when the subject is looking at the different feature stimuli or different pictures right here, for example, bottle as one of the category and shoe as another category. And now we may extract the different voxels. Again, it is not necessarily that you have to constrain the voxel distribution with the neighboring region. You don't need to do so. In this picture, they actually extract different voxels from the different brain regions right here. However, you don't want to do this kind of a random extraction. You need to base on some kind of the prior information. So this is just kind of the demonstration right here. You don't need to constrain your brain region to a certain point. Okay. So in this case, we may extract the feature or extract the voxel signal or voxel activation value from different locations. So we take this example, we may have the n features right here, or for example, we say n equals 6 right now. So we take 6 voxel signal as the features right now. So we have V1, V2, V3 to the V6, okay? So right now, you can see we may let the subject experience the stimuli for 3 different rounds right here, okay? And again, based on the machine learning idea, we need to separate our data set into 2 different subsets. One for training model and another one for testing this model performance. Okay, so in this case, we may have 3 different rounds right here. And for each round, subjects will perceive or receive the stimuli of bottle and the shoes with equal numbers. Okay. And for the round 1 and round 2, we use them to train the model. And for the round 3, we preserve them to test the model performance right here. Okay, so right now, let's read this matrix. Actually, for different rows right here represent the signal level or baud level or activation level, anything you want, extracted from different voxels. So you can see when the subject is looking at a bottle picture, you can observe that actually for voxel 1, 2, 3, 4, 5, 6 different voxels, you may have different values right here. However, there is a pattern. Pattern means you can try to find the rule or the common rule between the different stimuli but the same category right there. So you can see for 3 different stimuli but they all belong to the bottles category right here, you may observe that, okay, voxel 1, 4, 5, and 6 may exhibit a gray color right here. But for voxel 2 and 3, they may have a brighter pixel level right here, okay, or voxel level right here. However, when subject is looking at the shoe picture right here, you may see the reverse pattern right here. Of course, this is just for demonstration, so pretty ideal situation right here. And again, you will retest the subject in round 2, you will find out the pretty similar pattern right here. However, they definitely have some kind of the variation from stimulus to stimulus. They will definitely exhibit it because of the noise or because of the slightly changed mental state that you may anticipate right there. And you will use this first 2 rounds. Now you try to use the machine learning model. For example, this may be the support vector machine. You try to understand for the category blue, that means the shoe picture, and the category red, that means the bottle picture right here. You try to project this so-called 6 feature or 6 variables or 6-dimensional information to another plane or to another projected plane that you can actually identify a certain boundary to say below this boundary they belongs to the blue category. Upper or above this boundary they are belongs to another category. So you try to transfer or project your data set into another data plane right there. Okay, or sometimes we say this is so-called hyperplane right there. Okay. So this kind of classification is actually done by machine. But you need to train machine with a proper feature set right here. So sometimes if you get a very, very poor result, it may not because you use a wrong model, but you use the wrong data set or wrong feature set right there. For example, you pick the wrong 6 voxels. They are irrelevant with the this kind of the mental state of these 2 different objects of representation right there. Okay, so you need to think about different things right here. And then finally, once you build up this kind of the optimal or ideal classification boundary right here, now you can input this round 3 as the test data set. So you can pick any of the, we say 6x1 feature factor right here as the input. And again, the model will transfer this kind of a 6x1 vector into this hyperplane right here. So you can identify whether the data set is below or above this kind of the boundary right here. Okay, so you can see even in round 3, we try to reorder the stimuli order right here. So you can see we start from the shoe stimuli right here, but you still can see the pattern will have the corresponding activation right here and for bottle right here. So now you just let the machine do the thing. Okay. So this is a basic diagram or the flow that you need to do. You need a proper solid design that give you sufficient sample. So you need sufficient blocks, you need sufficient rounds right here. Now you need to identify the feature. Then you need to find a proper machine to train with. Then you need to use this kind of machine to test on your test data set to confirm the performance. Okay. So this is a general idea. If you want to know the detail, just find this paper and this will tell you the detailed information. So for the machine learning model, in this case, we don't have that much time to introduce in detail, but I just try to use this one of the video produced by, I don't know how to say this, Zhao from the YouTube. Actually, this is around, I think, 3 minutes, but this girl, she just used plain English words to help you understand what is the basic operation or basic idea behind the SVM. Of course, they have the bunches of the equation or formula behind this. If you want to know, go find Professor Weeder, he will tell you. Okay. Okay. Anyway, I just try to play this video for you, and you just try to listen on this.
So let's start with, what is a support vector machine? Well, it's a classification technique. So what does that mean? So let's say we had all these blue dots and all these teal dots, and I asked you to classify this data. So another way to say that is if I had asked you to split the data. Well, what would you do? You could split the data this way, or this way, or this way. All of those ways work. But what if I asked you to split the data in the best possible way? Well, then you would probably say that this line best splits that data. So at the end of the day, that's essentially what a support vector machine is. It's this model that best splits this blue and teal sections. So why is this the best split? Well, let's say that that line in the middle there, that's the median of a road, and that these are the two lanes of the road. So in this case, this is the widest road that separates these two groups. So if we go back and look at some of those other lines that we had used to split the data, you can see that they create some pretty narrow roads. But this one here, this is the widest road that separates the two groups. So let's add in some more technical terms now. So instead of saying this is the widest road that separates the two groups, we can say that this is the widest margin that separates the two groups. Another way to say this is the distance between the points and this line are as far as possible. So again, these points here, these can also be called support vectors, and this line here, this can be called the hyperplane. Okay, so those are all our technical terms. So let's summarize all this again. If I had asked you to split this data in the best way possible, you can now say that this is the hyperplane that best splits the data because it's as far as possible from these support vectors here, which is another way of saying we have maximized the margin. Okay, so how do you maximize the margin? Well, this is actually a constrained optimization problem. So there's two parts there, the constraint and the optimization piece. Let's break it down. The reason that you're trying to optimize something is because in this case, we're trying to maximize the margin. And the reason that there are constraints is because our constraint here is that these dots here, they can't be on the road. They have to be away from the road. So we have our constraints and we have our optimization. So this is a constrained optimization problem. So the way to solve a constrained optimization problem is to use Lagrange multipliers, which involves quite a bit more math, so I'm not going to go through it here in detail.
Okay, so this is a quick introduction about the SVN. Of course, SVN, the real value behind SVN is actually the cost function and the kernel trick. However, if you really want to learn this, definitely you need to attend some courses about the machine learning, but not in this one, okay? And before we go into the second part about how to actually perform the MVPA using a demo data set, I'd like to introduce, I think, two more different things that you should know. Then there is a late developed approach we called Searchlight Approach that actually developed in 2006 by this group and published in PNAS journal right here. So actually for the Searchlight Approach, they try to identify where in a brand does the activity pattern contain information about the experimental condition. That means for this kind of things, why they call Searchlight? Because they don't have the prior information or the idea about which part of a brand is the key portion or key part to represent the different brand mental state or something. So the Searchlight approach is actually trying to iteratively or repeatedly perform the classification or machine learning approach by moving your feature set. That means in the very beginning, you may start from this voxel group right here. You use them as the feature set to perform the analysis. However, if the result is not that good enough, then you will shift your feature set to another group. So you try to search all the brand regions with different voxel set or feature set to identify which part of the brain may bring the most important or most valuable information to help you differentiate the experimental condition right here. Okay, so this is so-called Searchlight Approach. So this is a little bit different that normally we use the GLM model that we actually try to find out the activated region. How we define the activated region, that we try to perform the GLM, that we use the statistical analysis on the beta value. That means the coefficient of the regressor. We try to identify which part, which voxels of the brain may have the significant correction coefficient or the regression coefficient with the study design. Then we can claim that actually this voxel or this brain region may activate during this kind of experimental situation. Okay. However, this kind of things we may use the spatial smoothing to improve the SNR, and in this way is that simply we try to ignore, or we don't think that the correlation between voxels or the pattern between voxels is that important. So we can use the smoothing approach to get rid of these kind of things. We try to using a smoothing approach to get rid of the noise interference right there. However, based on the Searchlight approach or MVPA, Searchlight is just kind of the extension of the MVPA. This is kind of the, we try to identify the informative region. What is the informative? That means this region can provide the information to help us differentiate the different experimental conditions. Now, we don't use the activation term, we actually use the informative region right here. So we try to compare the activity patterns within this kind of visual set or voxel set as the distributed representation for our brain when the subject perceives different kind of the stimuli right here. So this is so-called multivariate statistics, okay? So this is two different roadmaps. However, based on the result published in this paper, you may find out they may have a very similar pattern in spatial distribution right there. In the very first one, this is a smooth data set. Let me zoom in for you. This is a smooth data set with the GLM analysis. So of course, you can identify the activation region based on what we did in GLM section right there. However, you can also perform the Searchlight approach that I just try to move over different brain regions, and I try to give the score that whether this region or this voxel set may provide useful information to differentiate the different experimental condition. If yes, again, I may give you a significant color right here. For example, the yellow color right here. So I can say this is the most informative region, and this is actually the most activated region right here. But you can compare these two different maps right here. They come from different approaches. However, you still can find out actually the activation region may also highly correlated with the informative region. This is very interesting things. And now you can try to compare this B map and the C map. You try to use the overlapping idea right here. So now you can see if you find the intersection right here, it will give this kind of color. So you can see this color actually occupy most of the identified region right here. So most of the map B and C actually overlapping with each other. However, you still can find out there is some region only observed within the activation-based measure and only within the informative-based measure right here. So you can see this tells us that these two different regions may help you elucidate or help you to understand brain state. However, they may also reveal some different information. So this can be kind of the complementary measure that it can help you to further discuss whether the brain state is currently in. So for this kind of a Searchlight, they actually use so-called the spherical multivariate Searchlight. That means you will use a spherical region and move it. And the optimal radius is around 4 millimeter, contains around, when you use the 2 by 2 by 2 isotropic voxel right there, they will contains around 33 voxels right here. So each 33 voxels will become the feature set for the machine learning analysis right there. Okay. So for this kind of things, the resultant map is actually reflect how well this multivariate signals, or how well these features set in local spherical neighborhood can differentiate the experimental design right here. Okay, so this is the idea about the searchlight. And the final thing is the pattern similarity analysis. You can not only use these kind of things to classify the brand state, you can also use this kind of idea to discuss the correlation when our brand looking at different things right here. For example, you can pick a different region. We may pick this region as an example. When you look at the male human face and the female face right here, you can find out actually this is the color coded with the dissimilarity. So lower dissimilarity means they have a high correlation, okay? And a high dissimilarity means they have a lower correlation right there. So you can see when subject is looking at the male face and the female face, they actually have a very high correlation. Okay, so the gender make a little difference between these two different stimuli. And when you're looking at the building right here, there may be different building, however, you can induce a pretty similar pattern right here. But when you compare the human face with a building, this similarity becomes very high. That means lower correlation right here. You can also represent this kind of the correlation with this kind of the similarity graph icon. That means closer icon means they have a higher correlation. Distant icons right here, that means they have the lower or smaller correlation right here. So I think the previous searchlight approach and this pattern similarity analysis is kind of the extended version or extended approach that originated from the MVPA. So you can think about this. This can help you to compare between regions, brand regions, species, mental states, and even the disease states right here. Okay, so for the last slide in this section, I try to let you know that the available toolbox for MVPA analysis right now, you have one called PyMVPA. It's actually built in the Python environment. And you have three other different approaches actually building in the MATLAB environment. So there is one called Princeton MVPA Toolbox, Pronto right here, and another one called Cosmo MVPA right here. And today we are going to introduce this one because only this one has the graphic user interface. That means you can easily to perform this kind of analysis. However, this one and this one only provide the source code of the MATLAB code right there. So if you are familiar with MATLAB coding, you can try to find this one and this one. And there is one more thing I'd like to emphasize is that you can see this toolbox, Cosmo MVPA, is actually released in 2016. This is the most up-to-date one, and you will find out actually the searchlight approach and the pattern similarity analysis is only available in this toolbox. Okay, so today, although we use this one, but it's simply because they provide a GUI. However, the extended analysis, you need to use this Cosmo MVPA. Okay, just for your information. Okay. So right now we take 5-minute break right here, and then we will come back for this second point.